At 0215 hours local time, amidst the freezing darkness of the Siberian taiga, a lone figure trudged through knee-deep snow toward a seemingly insignificant gray metal box beside the Russian railway's main line that forms part of the Trans-Siberian Railway corridor. Frost hung in the air like suspended glass, each breath crystallizing instantly in the sub-zero stillness. The metal cabinet stood half-buried in snowdrift, unremarkable to any passing observer. Just another utility fixture along thousands of kilometers of steel track. But this was an SCB relay cabinet, the central nervous system of Russian military logistics. While the Russian military command focused heavily on protecting ammunition depots and airfields, they largely ignored these thousands of isolated cabinets scattered across the vast expanse of the country. The intruder knew exactly what this box contained and how fragile the entire supply chain truly was. The Russian armed forces rely on the railway network to transport over 60% of all their heavy military equipment, artillery shells, and fuel to the front lines. Unlike highways, which quickly degrade under armored weight, railways distribute mass efficiently over hardened steel rails and reinforced beds. The railway operates on a block signaling system, dividing the massive track into sections measuring roughly 2 to 3 kilometers each. Each relay cabinet controls the traffic lights and automated switches for its specific block, ensuring that no two massive freight trains ever occupy the same section of track simultaneously. In essence, every cabinet functions like a neural node in a continental-scale organism, constantly transmitting, receiving, and calculating the safe choreography of iron giants moving through darkness. Deep inside a regional dispatch center located 400 kilometers away in Novosibirsk, a railway controller watched a massive illuminated board tracking dozens of supply trains. The room hummed softly with electronics, glowing LEDs reflecting off glass panels covered in schematic track diagrams. Train number 472, pulling 70 heavily loaded cars of artillery ammunition and diesel fuel, was currently moving west at a steady speed of 75 kilometers per hour. The controller relied entirely on the electronic telemetry provided by the remote relay cabinets to monitor the safe progression of these high-priority military deliveries. Colored lines shifted across the board, each one representing thousands of tons of moving steel. A single freight train of this massive size weighs approximately 6,000 metric tons, meaning it carries an immense amount of kinetic energy. According to the fundamental laws of physics, stopping that much moving mass requires an enormous amount of friction and distance. Even under ideal conditions, engaging the emergency brakes at full capacity means the train will still slide forward for at least 1.5 kilometers before grinding to a complete and total halt. That distance increases dramatically in freezing weather, when steel wheels meet rails polished by ice crystals. The automated signaling network is meticulously engineered specifically to account for these massive braking distances, keeping the iron giants separated by invisible safety buffers calculated down to the meter. Back in the freezing taiga, the saboteur pried open the door of the relay cabinet using a heavy steel crowbar, the metal hinges groaning briefly before surrendering. Inside, neat rows of electromagnetic relays, copper bus bars, and thick communication cables filled the enclosure like the exposed circuitry of a mechanical brain. Instead of explosives, which were incredibly difficult to smuggle across the country and highly visible to security forces, the operative carried a simple incendiary mixture. They methodically applied a thick layer of thermite paste directly onto the main processing boards and the primary power distribution terminals. Thermite burns at an astonishing temperature of over 2,200 degrees Celsius, which is more than hot enough to effortlessly melt right through copper wiring, thick steel brackets, and sophisticated microchips in a matter of seconds. At exactly 0220 hours, the saboteur ignited the chemical mixture and immediately retreated into the dark tree line. The reaction began silently. No explosion, no dramatic flash, just a blinding white flare that hissed like a cutting torch. Within 30 seconds, the intense thermal reaction completely vaporized the cabinet's internal logic boards, instantly severing the electronic handshake between that specific track block and the regional dispatch headquarters. Molten copper dripped like liquid fire onto the snow below, freezing into twisted metallic sculptures. The moment the relay cabinet's circuitry melted into a pool of glowing slag, the railway's fail-safe protocols automatically engaged across the entire sector. When the central server loses communication with a block cabinet, the system assumes the worst possible scenario and immediately defaults the signals to red to prevent catastrophic collisions. Inside the dimly lit cabin of train number 472, the engineer was staring into the darkness when the trackside signal suddenly flashed from green to a harsh, blinding red. He had exactly 3 seconds to react before the automated safety systems forcefully engaged the train's pneumatic braking sequence. The immense pressure in the brake pipe dropped instantly, forcing the heavy cast iron brake shoes against the steel wheels of all 70 rail cars simultaneously. Sparks showered into the snow as thousands of tons of forward momentum violently fought against the sudden application of mechanical friction. The agonizing screech of metal sliding against metal echoed through the empty forest as the massive locomotive desperately tried to bleed off its kinetic energy. Snow along the track vaporized into steam under the heat of friction, and a plume of metallic smoke trailed behind the skidding train like a wounded beast marking its path. The colossal freight train finally shuddered to a complete stop mere meters before entering the now dead track section, but the tactical damage was already done. In the Novosibirsk dispatch center, a cascading cascade of error warnings flooded the controller's main monitor. Red indicators blinked furiously across a 20-kilometer stretch of track. The destruction of just one relay cabinet essentially blinded the automated traffic management software for a crucial segment of the main logistics artery. Railway doctrine dictates that when electronic signaling fails, operators must switch to an archaic manual method using localized radio relays and paper documentation to authorize the movement of each individual train. This excruciatingly slow process reduces the maximum operational speed of the line from 75 kilometers per hour down to a crawling pace of just 15 kilometers per hour. Dispatchers must confirm block clearance verbally, log it by hand, and coordinate sequential movement with extreme caution. Within 45 minutes, a massive backlog began to form, as 6 additional westbound military supply trains were forced to halt on the tracks behind train number 472. Steel wheels stood frozen against steel rails, engines idling uselessly in the snowbound night. This single $10 thermite charge had just paralyzed the delivery of over 30,000 tons of heavy combat supplies. While the gridlock worsened, the Ukrainian operatives were already initiating the second, far more destructive phase of their silent sabotage campaign. They understood that burning signaling cabinets only caused temporary delays, usually resolved by maintenance crews within 12 to 24 hours. To create a permanent logistical nightmare, they needed to utilize the sheer weight and velocity of the trains as kinetic weapons against the infrastructure itself. 50 kilometers further down the line, another operative stealthily approached a manual switching mechanism near a tight curve in the track. The mathematical formula for derailment relies on the lateral force overcoming the gravitational weight keeping the train wheels securely seated on the steel rails. If a massive locomotive moving at 60 kilometers per hour suddenly encounters a switch that is only partially thrown, the flanges of the front wheels will forcefully strike the edge of the diverging rail. The immense kinetic energy has absolutely nowhere to go but outward, violently snapping the heavy steel track bolts and tearing the rail completely off the wooden ties. Steel under compression behaves predictably until its yield strength is exceeded, and then it fails catastrophically. The operative carefully unbolted the standard railway lock and wedged a heavy, custom-machined piece of hardened steel between the switch point and the stock rail. This nearly invisible modification forced the heavy switching rail to remain open just 5 centimeters, a tiny gap that would be completely imperceptible to a train engineer hurtling through the darkness, but mathematically devastating to the wheel assembly. Frost quickly formed over the altered hardware, concealing the tampering beneath a natural veneer of ice. At 0340 hours, train number 511, carrying 40 flatbed cars loaded with newly refurbished armored personnel carriers, approached the compromised curve. The locomotive's massive headlight cut through the falling snow, illuminating only a narrow tunnel of swirling white. The engineer saw absolutely nothing amiss on the tracks ahead. The train entered the curve at 50 kilometers per hour, generating immense lateral centrifugal forces that pushed thousands of tons of weight heavily against the outer rail. In less than 0.3 of a second, the leading left wheel struck the 5-centimeter gap with the force of a bomb going off, instantly riding up and completely over the steel track head. The massive 120-ton locomotive violently left the rails, its enormous steel wheels grinding directly into the frozen gravel ballast beneath the track bed. Gravity and momentum instantly transformed the train into a highly destructive plow, tearing up wooden ties and concrete sleepers for over 200 meters. As the locomotive aggressively dug into the frozen earth, its rapid deceleration created an unstoppable kinetic shockwave that violently rippled backwards through the remaining 40 flatbed cars. The heavy couplings holding the massive cars together instantly snapped under the immense compressive forces. The first 10 flatbeds, carrying newly refurbished armored personnel carriers, violently jackknifed, slamming into one another with the force of an artillery barrage. The 60-ton military vehicles snapped their heavy retaining chains like brittle twigs, tumbling off the flatbeds and crashing heavily into the adjacent snow-covered ravine. Twisted steel, splintered timber, and shattered machinery formed a tangled monument to momentum unleashed. Inside the regional dispatch center in Novosibirsk, the nightmare scenario unfolded across the main tracking monitors in real time. The sudden loss of telemetry from train number 511 immediately triggered a catastrophic system-wide alert, completely halting all eastbound and westbound traffic across a 150-kilometer radius. The chief dispatcher frantically attempted to hail the derailed train via the encrypted radio network, but the locomotive's primary communications array had been completely crushed beneath 90 tons of twisted steel. This was not an isolated incident, but rather a highly coordinated logistical decapitation strike. Within a single 3-hour window, the Ukrainian operatives had simultaneously triggered identical sabotage protocols at 7 different strategic choke points across the Trans-Siberian network. The mathematical probability of 7 simultaneous, catastrophic mechanical failures occurring naturally was practically zero. Patterns emerged across the control board like spreading cracks in glass. The Russian Military Logistics Command now faced an impossible mathematical and engineering crisis. Clearing a multi-train derailment deep within the isolated Siberian taiga requires highly specialized heavy recovery cranes, which move strictly by rail, because the tracks were completely severed on both sides of the massive wreckage. Bringing these massive 150-ton railway cranes to the exact crash site became a monumental logistical paradox. To fix the broken track, they desperately needed the trains. But to move the trains, they absolutely needed the unbroken track. Engineering doctrine states that replacing 200 meters of completely shredded track bed in sub-zero winter conditions takes a dedicated crew of 50 men, at least 48 hours of uninterrupted labor. Frozen ballast must be excavated, new ties laid precisely, rails aligned to millimeter tolerances, and the entire section reballasted and compacted before safe passage can resume. But with 7 separate derailments blocking the primary logistics arteries simultaneously, the repair timeline rapidly expanded from days into weeks of total operational paralysis. 4,000 kilometers away on the active front lines, the immediate consequences of these silent taiga strikes materialized as a sudden and catastrophic starvation of combat resources. Russian artillery batteries, which routinely consumed over 10,000 heavy shells every single day, suddenly received orders to strictly ration their rapidly depleting ammunition stockpiles. Fuel convoys were delayed, armored units idled, and offensive operations stalled for lack of logistical continuity. The frontline commanders were completely unaware that their desperately needed resupply trains were lying twisted and broken in a freezing Siberian ravine. This brilliantly asymmetrical warfare strategy cost the Ukrainian operatives less than $5,000 in basic thermite, crowbars, and custom-machined steel wedges. In direct contrast, the resulting physical damage to the Russian locomotives, the destroyed armored personnel carriers, and the completely ruined railway infrastructure easily exceeded $150 million in immediate, unrecoverable material losses. The ratio of investment to destruction was staggering. The Russian Interior Ministry fundamentally misunderstood the sheer scale of the vulnerability they were attempting to secure. The Russian railway network spans over 85,000 kilometers of track, passing through some of the most remote and inhospitable terrain on the entire planet. To properly guard every single relay cabinet, switching station, and blind curve against specialized sabotage teams would require deploying over 200,000 dedicated security personnel away from the active front lines. It was a mathematically impossible defensive equation. Saboteurs did not need to win massive bloody battles or destroy heavily guarded fortresses to effectively cripple the Russian war machine. They simply needed to persistently exploit the fragile physics of massive moving objects and the completely undefended electronic nervous system of the railway, in a conflict defined by artillery barrages and armored thrusts. The most devastating blows were sometimes struck silently, in darkness, against unguarded steel boxes half buried in snow. The silent war in the deep taiga continued uninterrupted, bleeding the massive logistics network dry one severed relay at a time. In Novosibirsk, emergency coordination cells worked without pause, drafting contingency routing plans that strained secondary branch lines never designed to handle such concentrated military throughput. Aging tracks groaned under redirected weight, and maintenance crews reported accelerated wear on rails already brittle from extreme cold. Each improvised workaround solved one bottleneck while quietly creating two more, compounding systemic fragility. Insurance assessors and defense accountants attempted to quantify the cascading losses, but spreadsheets failed to capture the strategic cost of time. Every stalled train represented not only destroyed hardware, but deferred offensives, missed artillery windows, and shifting battlefield momentum. In modern industrial warfare, logistics is tempo, and tempo once lost cannot be easily reclaimed. Rumors spread among railway workers stationed along remote sectors of track, many of whom had never before considered the cabinets beside them as potential targets. Some began conducting informal patrols during night shifts, scanning the tree lines with flashlights, listening for unfamiliar sounds in the forest. Yet the sheer geographic scale dwarfed any grassroots vigilance. Vigilance without density offered only illusionary security. Far from the frozen wreckage, military planners were forced to confront a sobering equation. Protecting every kilometer of rail would require resources rivaling those deployed at the front itself. The conflict had expanded into infrastructure, mathematics, and probability. Steel, electricity, and momentum had become weapons, and the battlefield now stretched invisibly across the vast Siberian night.